Welcome viewers to the fourth segment of the fourth lecture for the online series of lectures for the course of Algebraic Topology 2. Towards the end of the previous segment, we stated Theorem 4 related to the exact homology sequence of a pair and saw its application in terms of an example. Now, we'll begin this segment by a lemma called the Zig Zag Lemma. Let me state the Zig Zag Lemma first and then I'll prove it. The Zig Zag Lemma. Well, before stating it, I think it's worthwhile to state a definition. But why do we need Zig Zag Lemma? We actually prove Theorem 3, and we shall reformulate the result of Theorem 3 as a theorem about chain complexes and prove it in that form. Then for the special case of the complex K, it's some complex K0 and the pair K comma K0, Theorem 3 will follow automatically. Okay. All right, so let's get to the definition. Let calligraphic C, calligraphic D, and calligraphic E be chain complexes. We know what chain complexes are. Let 0 denote the chain complex whose groups vanish in every dimension. Let phi from calligraphic C to calligraphic D and psi from calligraphic D to calligraphic E be chain maps. We say the sequence 0 to calligraphic C, and then from C to calligraphic D, and then from D to calligraphic E, and then from E to 0, where the chain map phi from C to D, the chain map from C to D is denoted by phi, and the chain map from D to E is denoted by psi. So what do we mean by this sequence being exact? So this sequence is exact, or that it is a short exact sequence of chain complexes, short exact sequences of chain complexes if in each dimension P the sequence zero to C sub P, from C sub P to D sub P, from D sub P to E sub P, and from E sub P to 0. So the homomorphism, group homomorphism from the group CP to DP is 5P, and the group homomorphism from DP to EP is the is denoted by psi p. So this sequence is supposed to be an exact sequence of groups, is an exact sequence of groups. Okay, so if these sequences for every p are exact sequences of groups, then we say that the sequence of chain complexes is an exact short exact sequence. Okay, for example, if K is a complex and K0 is a subcomplex of it, and C of K is a chain complex, whose underlying groups are the chain groups and the homomorphisms are the boundary maps del P, then the sequence 0 to C of K0 to C of K to C of K comma K0 to 0 is exact. Okay, it's because Cp of K comma K0 is a quotient group of Cp of K modded out by Cp of K0, and this is by definition. This holds by definition. Okay, now it's time to state the zigzag lemma, which we call lemma 3. Okay, let me erase everything. Lemma 3, the zig zag lemma. Suppose one is given the chain complex one is given the chain complexes calligraphic C, which is the collection of the groups Cp and the homomorphisms del Pc, the chain complex calligraphic D, which is the collection of the groups dp along with the homomorphisms del pd, and calligraphic E equal to E sub p del pe, and chain maps phi psi such that the sequence 0 to calligraphic C to calligraphic D to calligraphic E to 0, and the chain map between C and D is denoted by phi, and the chain map between D and E is denoted by psi, such that this sequence is exact, then there is a long exact sequence, long exact homology sequence, H HP of calligraphic C to HP of calligraphic D to HP of calligraphic E. This is phi P star. This is it's better to call it, I don't know. This is phi star at P. Okay. This is I don't know. I think we were right before. This is phi P star. This is psi P star. You have to do it this way, for the because we will need this notation later during the proof. For that reason, we are writing it as phi P star instead of phi star at P. Okay. All right. And then from here to here is the map del star at P, as was done previously. And this is HP minus 1 at C, and then from HP minus 1 C of C to HP minus 1 of D, and goes on like that. And this is what? Phi P minus 1 star. Okay, this is the exact homology sequence where delta star at P is induced by the boundary operator in calligraphic D. Okay, now we can start the proof. Okay, let me erase everything. So that this is the statement of Zig Zag Lemma. We need to prove it. Proof. The proof is of a type now commonly known as diagram chasing. Okay, this technique of proof is called diagram chasing. It is a very useful technique in algebraic topology, and you should master this technique through the proof of this zigzag lemma. So we are going to use the following commutative diagram. Let me draw this commutative diagram on the right. I'm not going to erase it because I need it for the subsequent steps to follow during this proof. So 0 to C sub P plus 1, and then C sub P plus 1 to D sub P plus 1, and then from D sub P plus 1 to E sub P plus 1, and then from E sub P plus 1 to 0. This is one short exact sequence, and This map is 5p plus 1. This map is psi p plus 1. And d sub p plus 1 is an element in big D p plus 1. Similarly, small e sub p plus 1 is an element in E sub p plus 1. Then from 0 to C sub p, and then from C sub p to D sub p, from D sub p to E sub p, and then from E sub p to 0. This is delta p plus 1 superscript c. This is delta p plus 1 superscript d, and this is delta p plus 1 superscript e. Now I take a generic element small c sub p of Cp, and dp is an element in big dp, and E sub p is an element here in big E sub p. This is 0 to Cp minus 1, and then from Cp minus 1 to dp minus 1, and then from dp minus 1 to ep minus 1, and then from ep minus 1 to 0. This is del p c. This is del p d. This is del p e. This is c sub p minus 1. This is phi sub p. This is psi sub p. This is phi p minus 1. This is psi p minus 1. From Cp minus 1 to Cp minus 2, this is 0. This is delta p minus 1 superscript c. Then from Cp minus 1 to from Cp minus 2 to dp minus 2, and from dp minus 2 to ep minus 2, and from ep minus 2 to 0. This is phi p minus 2. This is del p minus 1 superscript d. This is del p minus 1 superscript e. This is phi p minus 2, and this is psi p minus 2. Okay. So this is a commutative diagram, and we are going to use this commutative diagram. So this is the figure 3. This is diagram chasing. Okay, so step 1. Step 1 of the proof. First, we define this map, homology boundary homomorphism, del star at P. Given a cycle E sub P in the group EP, okay, this is an element here, okay, an element here. So this belongs to the kernel of this map because it is a cycle, right? An element of kernel of this map del P superscript E. Choose dp in the group big dp. Okay, here we choose a group element so that psi p of dp is equal to ep. Okay, so we start with the cycle ep belonging, which is a group element in big ep, and we assume that this is a cycle, right? EP, the group element EP in big EP is a cycle, and hence EP belongs to the kernel of this map. And of course, there is an element DP in big DP such that psi p of DP is EP. It can always be done since psi p is a surjective map or an epimorphism. It can always be done since psi p is surjective. Okay. Now the element del p d dp. Okay, dp is the element in big dp here, and del p dp is here in dp minus 1. So the element del p dp of dp minus 1 lies in kernel of psi p minus 1. Okay, psi p minus 1 is this map, so it lies here in the kernel. It's a subgroup of dp minus 1, kernel of psi p minus 1, and this guy has to lie in the kernel of that map psi p minus 1. Why? This is because psi p minus 1 del p d dp, now we use the commutativity of the diagram, is equal to, look at this, so we are going where? So we are going from dp to ep minus 1 via this path, and it is the same as taking the other path here. All right. So psi p minus 1 composed with del p d is the same as del p e composed with psi p dp, right? But we know that psi p dp is equal to ep, so this is nothing but delta PE EP, right? And this has to be 0 because EP is in the kernel of del PE, or in other words, EP is a cycle. EP is in kernel of del PE. Okay, good. Now since kernel of psi p minus 1 is equal to image of phi p minus 1, kernel of this map is the same as the image of this map. Using the exactness of this sequence, we see that there exists C sub p minus 1 in big Cp minus 1 such that phi p minus 1 of Cp minus 1 okay equal to so this guy is in kernel of psi p minus 1, and we know that the kernel of psi p minus 1 is equal to the image of phi p minus 1. So of course there exists an element Cp minus 1 here such that phi p minus 1 Cp minus 1 is equal to this guy del p d dp. This is our equation number 11. This element Cp minus 1 element Cp minus 1 is unique since phi p minus 1 is injective. From the exactness of the sequence, we know that phi p minus 1 is injective. Okay. So we obtain Cp minus 1 here, which is a unique element. It's important that Cp minus 1 is unique because phi p minus 1 is injective. Also, since phi p minus 2 acting on del p minus 1 c Cp minus 1 okay, Cp minus 1 is here, and this is acted upon by del p minus 1 c, which will be here, right? And phi p minus 2 acting on that element of Cp minus 2 using the commutativity of this square gives us del p minus 1 d composed with phi p minus 1, right? Phi p minus 1 at Cp minus 1. And this is nothing but del p minus 1 d composed with del p d dp using 11. and this has to vanish, right? Because this guy is identically 0 from the property of boundary maps. What does it mean? Okay, and further to this, phi p minus 2 is an injective map, and hence this guy has to be 0. So we get del p minus 1 cp minus 1 is equal to 0. So we have proven that this cycle here, this is a cycle, Cp minus 1 is a cycle, right? That's why we have gotten this. Now let me erase this part. I'm not going to erase the diagram. I'm going to keep it for a while since I'm going to need it for the rest of the proof. So we are going to define del star at P acting on the class homology class represented by EP to be equal to Cp minus 1, the class of Cp minus 1. This is our equation number 12. So this is a p cycle of the complex E that is not a p boundary. P cycle of the complex E that is not a p boundary. That is not a p boundary. And this one is a p minus 1 cycle here, a p minus 1 cycle of the complex calligraphic C that is not a p minus 1 boundary, not a p minus 1 boundary. So that is how we define this boundary operator. Now step 2. The first step was to define this operator delta star p that takes the homology class from here to the homology class here. Okay, it's a zigzag process. We show delta star at P is a well-defined homomorphism. Well-defined homomorphism. Okay, so we let EP and EP prime be two elements in the kernel of the map del PE, which takes EP to EP minus 1. Okay, this map. So EP and EP prime both belong to the kernel of this map del PE. Now choose dp and dp prime in the group big dp such that psi p dp is equal to EP and psi p dp prime is equal to EP prime. Okay, so first we choose EP and EP prime in the kernel of the map del PE, and then we choose dp and dp prime in big dp such that psi p of dp is EP and psi p dp prime is EP prime, right? Then choose CP minus 1 and CP minus 1 prime in big CP minus 1 here. So that phi p minus 1, this map, phi p minus 1 of CP minus 1 is equal to del P D dp and phi p minus 1 C prime p minus 1 is equal to del P D d d prime p. Okay, to show that del star p is well defined, we suppose EP and EP prime are homologous, so that both of them belong to the same homology class. Okay, that is, they belong to the same homology class, belong to the same homology class. We need to show that Cp minus 1 and C prime p minus 1 are also homologous. Then we are done proving that this map del star at P is well defined. Okay, all right. Let me erase this part again. I'm going to keep the figure intact. This is 0. Okay, so we assume that EP and EP prime are homologous. So, in other words, EP minus EP prime is equal to del PE, is equal to del P plus 1E, okay, EP plus 1 for some element EP plus 1 here in EP plus 1. This is equation number 13. Choose dp plus 1 here in this group big D sub p plus 1 such that psi p plus 1 acting on dp plus 1 is equal to e plus 1. It can always be done since psi p plus 1 is surjective, right? So that every element e sub p plus 1 has a pre-image here in dp plus 1. Psi p plus 1 is surjective. Then psi at p acting on dp minus dp prime minus del p plus 1 d dp plus 1. What is this guy? This is equal to because psi p dp is ep, right? Psi p dp is ep and psi p dp prime is ep prime and psi p composed with del p plus 1d is the same as del p plus 1e composed with psi p plus 1. So we can write del p plus 1e composed with psi p plus 1 acting on the same element dp plus 1. It's from the commutativity of this square. It follows from the commutativity of this square. Okay, now this is equal to EP minus EP prime minus del P plus 1 E, and what is psi P plus 1 dP plus 1? EP plus 1. So this is just E sub P plus 1. Okay. Now, using equation 13, we see that this is 0. Using 13. Okay. Therefore, one immediately finds that this element dp minus dp prime minus del p plus 1 d dp plus 1 is in the kernel of psi p. Since kernel of psi p is equal to image of phi p, kernel of psi p is equal to the image of phi p, all right, one must have phi p of cp is equal to dp minus dp prime minus del p plus 1 d dp plus 1 for some cp in big CP. This is equation number 14. Then phi p minus 1 acting on del p c cp. Okay, so we are taking the square, commutativity of the square, phi p minus 1 del pc acting on cp is equal to del pd composed with phi p acting on the same element cp, and this is equal to del pd phi p cp. This is equation 14. Is phi p cp is del p dp minus dp prime minus del p plus 1 d dp plus 1 using 14. So this is nothing but del p d dp minus dp prime, because this prime vanishes using the property of boundary operator. And according to the and according to the definition, according to the hypothesis, right, we chose cp minus 1 in such so that phi p minus 1 cp minus 1 is del p d dp, right? So from that we write del p dp as phi p minus 1 cp minus 1 and del p dp prime as phi p minus 1 c prime p minus 1, which is equal to phi p minus 1 cp minus 1 minus c prime p minus 1. Okay. All right, therefore one obtains the following. Therefore one obtains phi p minus 1. Since phi p minus 1 is a group homomorphism, one obtains phi p minus 1 acting on cp minus 1 c prime p minus 1 minus delta p c cp is equal to 0. Since phi p minus 1 is surjective, right, one must have delta p c cp is equal to cp minus 1 minus c prime p minus 1. Right? This is equation number 15, and 15 leads to the fact that cp minus 1 and c prime p minus 1 are homologous. Okay, so this establishes the well-definedness of the map del star at P. Okay, now to show that del star at P is a group homomorphism, note that psi P dp plus d prime p is equal to ep plus e prime p and phi p minus 1 cp minus 1 plus c prime p minus 1 is equal to del p d dp plus del p d dp prime is equal to del p d dp plus dp prime. This is equation number 16. Okay. So in the light of equation 16 and the definition of del star, one finds that del star EP plus EP prime is equal to CP plus 1 plus C prime P plus 1. Oh, I think I made a mistake here. It has to be CP minus 1. Why did I write CP plus 1? It has to be, so let me CP minus 1 plus C prime P minus 1. Okay, and this gives us Cp minus 1, the class of Cp minus 1 plus the class of C prime P minus 1. Okay, no Cp plus 1, Cp minus 1. It needs to be corrected in the notes. So it follows from the well-definedness of addition between equivalence classes. Addition between equivalence classes. So the equivalence class of two representatives of two equivalence classes is the sum of the two equivalence classes. Okay. So it means that this is del star EP plus del star E prime P. Okay, so we are done proving that del star at P, we should better write it at del star at P, del star at P, del star at P. So we are done proving that del star at P is a well-defined group homomorphism. Okay, from from HP of E to HP minus 1C. Good. Now step 3. So let me erase. So the second step is done. This is step 3. We now prove the exactness at HP of t. So on the right here, I draw the long exact homology sequence. It will be required now. This is HP of calligraphic C, and then from HP of C to HP of calligraphic D, this is 5P star, and then from HP of D via psi P star to HP of E, and then there is this map, the one that we constructed in step 1, del star P. It takes us to HP minus 1C, and then from HP minus 1C to HP minus 1D via this map phi P minus 1 star, and goes on like that. Exact long homology sequence. Okay, and we need to prove that it's exact. So we first prove the exactness at HP of t here. We now prove exactness at HP of t. That is, we prove image of 5p star is equal to kernel of psi p star. Okay. All right. Let's see how we do that. Let gamma be an element of HP of t. Since the sequence 0 to calligraphic C, from calligraphic C to calligraphic D via the chain map phi, and then from calligraphic D to calligraphic E via the chain map psi, and then from calligraphic E to 0 is exact. Since the sequence is exact, and from exactness we have kernel of psi p equal to image of phi p for all p. It means that psi p composed with phi p is equal to 0 for all p. One does have one does has psi p composed with phi p star, the induced homomorphism at the level of homology groups, is equal to psi p star composed with phi p star. So we did not discuss it earlier, but it follows from the functoriality of the induced homomorphism, from the functoriality of the induced homomorphism of homology groups. Okay. For details, refer to section 18 of the book by Moncrief, Elementary Elements of Algebraic Topology, okay, the one that we are following. So this holds. It implies that psi p star composed with phi p star is equal to 0. This is equation number 17. Thus, if gamma is in image of phi p star, okay, gamma is here. We chose gamma to be here. Now, if gamma is in phi p star, then from 17 it follows that psi p star gamma is equal to 0, right? Okay, so it means that image of phi p star is contained in kernel of psi p star. So gamma is an image of phi p star means that gamma is equal to phi p star alpha, right? For some alpha in HPC, for some alpha in HP of C. We see that psi p star composed with phi p star of alpha is going to be equal to 0, right? And then we replace it with gamma, so that psi p star of gamma is equal to 0, right? It proves that image of phi p star is contained in kernel of psi p star. Now let me erase everything here. Now let gamma is equal to the class of dp, and suppose psi p star of gamma is equal to 0. Okay, so phi p star. Now look at this diagram chasing figure, and since dp is in kernel of del pd modded out by image of del p plus 1d, so that del p d dp is equal to 0, right? One therefore has psi at p minus 1 composed with del p d dp commutativity of this square gives us this is equal to del p e composed with psi p acting on dp, right? And this is 0. So gamma is this guy. Gamma belongs to this group HPD. Okay, I think it's better to take a break at this moment and let me think about it, and I'll get back to you in the next segment. Thank you very much for attending this fourth segment.